So now we're moving on to the problems that are associated with weak acid titrations by strong bases. And so what we're going to learn here would just be flipped if you're talking about a weak base being titrated with a strong acid. So what we have here in this problem is they want us to calculate the pH, which is great. It's one of the reasons why we're doing a weak acid titration. There's sometimes less conversion back and forth between pH and pOH. They've given us a weak acid. If you weren't already familiar with formic acid, it is a weak acid. They also give us a strong base. If you weren't already familiar with it, sodium hydroxide is a strong base. They have to give us the Ka, or we have to go look it up in a table, as you'll probably have to do in the homework. Get that Ka so we know what dissociation constant or ionization constant is associated with the specific weak acid. They have to give us certain things like what are the concentrations. They give us the concentration of our acid, the concentration of our base. They've given us some starting volume of our acid, and then they're going to say, okay, we'll titrate in 2 or 3 or 4 different amounts of your base and tell me what the pH is after each one of those steps. Okay, so we are expecting that they have given us 4 places that fall along our titration curve. They've probably given us something at the initial phase. They have probably given us something in the buffer zone, maybe here, or maybe the midpoint, or maybe a little bit above the midpoint. They have probably given us a calculation that is with the equivalence point, and they have probably also given us something that is up here above the equivalence point. So they are drawing upon our knowledge of what's happening in each one of these steps so that we can use the appropriate equations to figure out what the pH is. And so let's walk through that step by step. So Part A said, let's do this calculation, and I just redacted the question, so it just says, Part A, 0.00 milliliters of our sodium hydroxide. So that means with no sodium hydroxide present, only the acid is going to matter. So we can think about this very conceptually. We have some beaker, it has our acidic solution in it. This has formic acid in it. Formic acid is a weak acid, so that means that we have a lot that has the H still on it, but we do have some instances where the proton has been liberated into solution, and that would leave an HCOO minus in solution. So this is a 50 milliliter solution, and the concentration is 0.100 molar of the acid. So what they're going to want us to do in this problem is add to this solution some amount of sodium hydroxide. In our example here, it's 0 milliliters of that sodium hydroxide. So that means that all that matters is what's happening already in the beaker. So we can write out the equation for what's happening in that beaker. So we've seen this before with our weak acids. They're going to set up an equilibrium. Our formic acid plus water is going to give us HCOO minus plus H3O plus, and that's what makes it the acid. So we have this equilibrium. An equilibria love ice table, so we can go ahead and start to fill in our ice table. And so we start with some amount of our acid. That was going to be 0.100 molar. Our water doesn't contribute to the table. We start off with 0 of each of our products. We're going to subtract some of the reactants, make some of the products, and bring that down, 0.100 minus X. Our X here, our X here. Our Ka equals the value that we looked up, 1.8 times 10 to the minus 4. We can set that equal to our equilibrium expression, or you might have remembered our shortcut and have jumped directly to this step. So when we get here, we recognize this is going to look like a quadratic equation if we go through and try to solve it. So instead, let's go ahead and try to make the 5% approximation. That means the 0.100 minus X term now becomes 0.100, and now we can solve for X. The calculator says that's 4.24 times 10 to the minus 3, and we can check to make sure that that 5% assumption is correct. And so when we do that calculation based on the ionization, 4.24% means we're coming in just under the wire, so that means that our assumption is going to work, and so we can just use that value up there in our ICE table. So we can go ahead and move it up. And so now we see that the H3O concentration is going to be that 4.24 times 10 to the minus 3. And so if we have the H3O concentration, we can go ahead and calculate the pH. And so when we do that calculation, the negative log of 4.24 times 10 to the minus 3 gives us a pH of 2.37. And so we'll probably want to remind ourselves that this was in fact the answer that we were looking for, and repeat it somewhere on the page. If they have asked us to calculate the pH, then we say yes, we have calculated that pH is going to be equal to 2.37, so we know that's the final answer. Draw a bubbly around it, do something, so we know that's the final answer. So now we move on to part B. So part B is going to be our weak acid, and we have gone ahead and added some strong base. So now we have added 15 milliliters of our strong base, and so we need to treat this like a neutralization. We previously did a neutralization, and we did it in two parts. The first part was to use moles in an ICE table so that we could figure out what was neutralized. What did you have left over? Did you have left over OHs, or did you have left over some H3O pluses? And once you had that, you were able to go in and use the Henderson-Hasselbalch equation so that you could calculate the pH. So let's see if we can use those same rules here. So I've redrawn that diagram so that now we can look and say, great, we still have a beaker. That beaker has 50 milliliters in it. It has our weak acid in it, so there's some that's still in the acid form with the H on it. There are some fewer number of molecules that have dissociated and made that counter ion, that in this case formate, HCOO, and some of the H pluses are in solution. Now this time they are asking us to add some sodium hydroxide, 15 milliliters, so I've drawn the 15 milliliters going in and what the concentration of that sodium hydroxide is. That clearly looks like it's going to be a neutralization, and when we have a neutralization, it's going to be the NaOH, that base, that is going to be neutralizing the acid. So we're not thinking about it going after the H pluses, we're thinking about it going after the acid that's available. So we can write out the equation for that neutralization reaction. And when we add that acid together with a base, neutralization is going to give us a salt, sodium formate, and water. And that's going to be the basis for our ICE table. But if you recall, when we were doing neutralization, we talked about a certain number of molecules of OH have to come together with a certain number of molecules of H+. So we're talking about moles, these molar ratios of things coming together. So we need to calculate moles of everything that we have in this equation. We can recognize that 0.200 molar sodium hydroxide means 0.200 moles of sodium hydroxide in 1 liter. But we don't have 1 liter, we have 15 milliliters, so we need to multiply it by the volume in terms of liters in order to get the number of moles. And then we can go ahead and add that to our ICE table. And we can do the same for our acid. We corrected for the volume, which was our 50 milliliters, or 0.050 liters, and so that's going to give us the number of moles of that acid HCOOH, and we can go ahead and move that into our table as well. So now we have moles of those starting reactants. And so now what we can do is say water is not going to contribute to our ICE table. When we start off this reaction, there was 0 sodium formate because there was no sodium around, right? So we're going to start that one off as 0. So now what we need to do is look at the acid and base that we're starting with and figure out which one is limiting. So 3.00 times 10 to the minus 3 is the smaller of the number. So we're going to call this the limiting reagent. And the limiting reagent always gets used up, so we're going to use all of it. We're going to subtract everything on the left. And we're going to add when we do stuff on the right of our arrow. So that's going to become plus 300 times 10 to the minus 3. And again, you'll see we kind of end up being a little more lax with sig figs when we're working these problems because all those decimal places sometimes are meaningful. and important to see small changes in our pHs. So great, so that means that we're going to cancel out our sodium hydroxide. That means we're going to end up with 2.0 times 10 to the minus 3 moles of that acid when we reach equilibrium, and we're going to end up with 3.00 times 10 to the minus 3 moles of our conjugate base when we're at equilibrium. So now we have moles. It would be great if we had concentrations, because if we had concentrations, we could actually use the Henderson-Hasselbalch equation in order to figure out the pH. So let's correct these for the volume. So our volume was 50, and we added 15 to it. So that is going to be a grand total of 65 milliliters. We can calculate the concentration of our formic acid by taking the 2.0 times 10 to the minus 3 moles, dividing it by those 65 milliliters, or 0.065 liters. That's going to give us a concentration of 0.0308 molar acid. And we're going to do the exact same thing to figure out the sodium formate concentration. And now that we have the concentrations of our acid and the conjugate base, we can in fact use the Henderson-Hasselbalch equation. And solving that gives us a pH of 3.92. So again, that was exactly what this question was asking us. It would probably be helpful if we said, yes, we did in fact solve this problem. pH equals 3.92. Draw something around it so we know that's the final answer. And so now we have a pH after we have titrated in some of that sodium hydroxide. So now let's move on to the next part. Part C was adding not 15 milliliters, but now they're adding, I believe, 25 milliliters. Yes, 25 milliliters. So this one, we need to go ahead and do that same neutralization table. I do want to say here that in this problem, you can potentially recognize that this is going to be a problem that's at the equivalence point before we ever get to the ice table. Once you get to the ice table, you're definitely going to see it's the equivalence point, but what I'm doing by eyeballing this is saying that if I have 50 milliliters of something that is 0.1 molar, that's going to be the same as 25 milliliters of something that is 0.2 molar. So that means that I'm actually adding the same amount of acid as I am base, which means that the acid and the base, the protons and the hydroxides, are going to counter each other out. So that means I'm automatically thinking I'm at my equivalence point, and so I'm expecting to get a pH that's going to be above 7, because in these titration curves for weak acid, strong base, that equivalence point is above a pH 7 because conjugate base is present, and that also means that my entire ice table is going to depend, my entire answer is going to depend on that conjugate base concentration. So all of what we're going to do here is going to be to try to get to that conjugate base. So I've started with my neutralization reaction. I'm going to use that as the basis for my ice table. I have to calculate the number of moles of acid and the number of moles of sodium hydroxide, and that's going to hopefully rapidly convince you that we're going to be at the equivalence point. So just like last time, 5 times 10 to the minus 3 moles of our acid, because we had 50 milliliters of 0.1 molar, and we're going to do the same calculation for our sodium hydroxide, and it should be a higher number of moles than last time, because now we have 25 milliliters instead of 15 milliliters. So now we've calculated the number of moles of both, and so you see that those are in fact equivalent to each other. 5.0 times 10 to the minus 3 moles of acid, 5.0 times 10 to the minus 3 moles of our sodium hydroxide. And just like last time, because we started off with just the acid and then added in that sodium hydroxide, we have 0 of that conjugate base present, and that water is not going to contribute to our ice table. So we're going to end up subtracting, they're both limiting, right? They're equivalent amounts. We're going to subtract 5.0 times 10 to the minus 3 from both of these, but that means we're going to add 5.0 times 10 to the minus 3 moles of that conjugate base. So 0 of our acid, 0 of those hydroxides, but yes, 5.0 times 10 to the minus 3 moles of that conjugate base. So that again is going to be a number of moles, but it's not going to be a concentration. We can calculate the concentration of this salt that we have made by just dividing it by the total volume. And our total volume now is going to be that 50 milliliters that we started with plus the 25 milliliters that we added, so a grand total of 75 milliliters or 0.075 liters. So when we do that calculation, we end up with 0.0667 molar. So let me update that figure. So now we have 0.0667 molar of this salt, and we have to ask ourselves, what's going to happen when this salt hydrolyzes? We had that as an entire lecture topic, so we know that we can break this down to see what would happen when this thing goes into solution. So we can look at sodium. When sodium tries to neutralize itself, what is the only thing that it can do? Is can grab an OH, and then that would leave an H+. Well, that's not going to happen, because if it forms sodium hydroxide is a strong compound, and so it's always going to dissociate right back. So this is not going to happen because this is strong. But what's going to happen if we look at the other case? In the other case, we're going to have HCOO- plus a water, and when it gets nearby, it's going to grab an H off of that water. When it does that, it's going to become the weak acid and an OH-. This is weak. And if it forms something that's weak, when it tries to neutralize itself, this is going to happen. So if this is going to happen, it is going to produce OHs. So we're expecting that at the end of this neutralization reaction, we're actually going to be a little bit basic. And we can set up another ice table based on the hydrolysis of this salt in order to figure out just how basic. So at the top, I've drawn out that chemical equation. I've started my ice table. I can go ahead and put in my starting concentration of the formate. So I've done that, 0.0667 molar of the formate ion. Water is not going to participate. We don't have any of the product at the initial time point. Our change, of course, is going to be our minus x and then a plus x and a plus x. Then we end up with our equilibrium line. So this is going to be a base dissociation. So we haven't calculated a Ka, we're actually working on a Kb. So Kb is going to equal the equilibrium expression, our x over our 0.007 times 1. And so this is what the expression would look like. Now this looks like where we have typically tried to use the 5% rule. We saw that the 5% rule applied when we were talking about formate going in the forward direction, which means that pretty much going in the backward direction it's going to apply as well. So we can actually say that this is approximately going to be equal to that x squared over 0.0667. So now we just need a value for that Kb. If you recall, as we went from the right side to the left side, that was our Ka. As we move from the left side to the right side, that's our Kb. And there's a relationship between a Ka and a Kb. So we know the Ka, right? We have already looked that up as 1.8 times 10 to the minus 4. So it's just going to be related to that Kb through the water ionization constant. So we see that Kb equals Kw over Ka, and we already know what Kw and Ka are. We do the math, we get 5.56 times 10 to the minus 11, and so we can use that value here. We can say that x squared over 0.0667 equals 5.56 times 10 to the minus 11. We can go ahead and solve for x. That calculation gives us 1.92 times 10 to the minus 6. So that is going to go up into our ice table for our OH minus concentration. If we have an OH minus concentration, we can get a POH. So we do that calculation and get a POH of 5.72. And if we have a POH, we can get a pH by subtracting the POH from 14. So finally, we get a pH, and that pH is going to be 8.28. And so going all the way back to the beginning of this problem, thinking about this being the equivalence point, and that the equivalence point of a weak acid titrated with a strong base needs to be on the basic side at that equivalence point, that means that this answer is going to be consistent with that expectation. We come in here and say, yes, we calculated that pH. pH equals 8.28. We draw something around it so we know that's the final answer. And all this work just to get to that equivalence point pH. So now in the final part D, we are looking at something that has more mils of sodium hydroxide than the equivalence point, and we know that because of the last problem, and then also because we could have actually looked at the 50 mils of 0.1 and said that would require 25 mils of the 0.2 sodium hydroxide to reach equivalence point. So we already know we're above that equivalence point. So when we look at this above the equivalence point or post equivalence point section phase of that graph, then what we're talking about is something that's going to be really dominated by the base that we've added. And so it's really just going to be the excess base, right? Because we have canceled out a lot of H pluses on those acids. We've canceled out all the acid. So whatever is left over after we cancel out that acid is going to be what contributes to the pH. It's going to be what gives us the OHs. So we can go in and we can just figure out how many moles of base have we added, how many moles of acid did we start out with, and what is our new volume. And so let's work that out together. So now we've calculated the moles of sodium hydroxide and the moles of that formic acid. And so that number for formic acid is just like last time, 5.0 times 10 to the minus 3. You see that that number is smaller now than the number of moles of sodium hydroxide. So we definitely have an excess of sodium hydroxide. So the difference between those two numbers is just going to be the subtraction is going to be 1.0 times 10 to the minus 3 moles of sodium hydroxide, which would be the same as number of moles of just those hydroxides. But we have to think about this not as the number of moles that's left over now, but we need to think about what is the concentration, because we need that in order to figure out POH and pH. And so in order to do that, we need to also think about how big is our volume now. So it is now 0.080 liters, or 80 milliliters, and so we're just going to divide those numbers. When we do that, we get 0.0125 molar solution of sodium hydroxide, so that's going to give us those hydroxide ion concentration. If we have that hydroxide concentration, we can actually get a POH. And once we have a POH, we can actually get a pH, because we can take 14.0 minus the POH, and that'll give us the pH. And so that calculation is going to give us a pH of 12.1, and so we can think about that in terms of our final answer being pH equals 12.1, and then we can also think about what this means for our overall graph. If we had plotted our titration curve, we'd have pH on that y-axis, and we'd also have increasing amounts of that sodium hydroxide on the x-axis. And so when we had 0 milliliters of that sodium hydroxide added, we calculated that we had a pH of 2.37. Now when we had added 15 milliliters of that sodium hydroxide, we bounced up to a pH of around 3.92. When we eventually got to 25 milliliters of that sodium hydroxide, we were up to 8.28, and when we got to 30 milliliters, we were up to 12.1. And so this isn't really drawn appropriately to scale, right, like the ones that we did, but we can anticipate what this curve would look like, right? Because the 8.28 was our equivalence point, and so we're expecting to have some type of vertical line there. We know this was a weak acid titration, so when we start off, we're not going to change that much. We're going to have kind of an area here where we might be a good buffer, and then it's really going to start to accelerate till we get to that equivalence point. And then after the equivalence point, at some point we level off. And so our curve would look something like that, again, with that buffer zone somewhere in here, with the midpoint somewhere like that, with our equivalence point somewhere like that in the middle of the flat, and then this is going to be that post-equivalence area up here. And so each region of this curve has its own kind of special considerations as to which type of procedure we should do in order to figure out what the pH is. And again, this would be the type of problem, not definitely 4 different points on this curve, but say 1 or 2 points on this curve that would let us know that you are able to reason through what's happening in this process and then apply the correct type of calculations to end up with that final pH. So that finishes this lecture. That finishes all the content in this chapter, and so you should have everything you need now to complete the homework 14A and 14B. Hopefully we've already worked through a fair amount of 14A because of all the previous lectures, and we can go ahead and move toward 14B for the homework and then also the associated quizzes. So you can go ahead and close this one and let me know if you have any questions about Chapter 14.